I see an Ivan. I spy an Ivan with my beady little eyes.
You guys do carry on quite a discussion recently, haven't you?
And then on Facebook, sometimes he just sort of hangs out and then creates a room for people to join and chat. We had like a 2-hour long chat about science and philosophy the other day. It was a lot of fun.
Yes, we see.
Ivan, can you hear us? All right, you're on mute.
Okay, it seems like your signal is getting a bit better now. It was in the red for a while.
Oh, really? I don't like being in the red.
Why not?
Well,
aren't we good at it?
I don't know. I'd rather be in the salmon.
Well,
hey, you guys are the ones with the accent, so.
What do we call it, Mr. Smartass?
When I have an accent, sometimes I have an accent drift.
Well, I have a basic problem of talking too fast and leaving out eyes.
Yeah.
Yeah.
here?
Looks like a Dave.
I'm
No,
gonna-
that's
that's
Mike.
Mr.
Hi, Ivan,
Alvaro.
Scott, Joanne.
Hello, Mike. How are you?
Hi
I'm
there.
very well, thank you. How are you?
So far, so good.
Will you please excuse me? I'm still eating.
I could complain, but who's listening?
Excuse me, I'm still eating lunch because I didn't realize the time until it was about 20 minutes ago. So, cheers.
Slandra.
Cheers.
Are we like half an hour early or are we on time?
We have 1 minute.
We have 1 minute. Toodaloo.
Creature down.
Miss John. Hello, John.
Moshi moshi.
How are you?
Hi, John.
I'm good.
I guess we're all here.
Ivan.
Yeah, Abby's not going to be able to join us today.
I'm still eating lunch, but you can put up with that, I
Me,
suppose.
me too, actually. I
Well,
think.
the two of you are still munching.
Just coffee.
Lunch at 3 p.m.
2 p.m. for me.
Oh, you're.
It's been it's been a busy day. The refrigerator broke last week, and so today was the day we got a new refrigerator, and it takes a
Oh.
long time to set up a new refrigerator.
Oh, really?
Well, you have to unpack all the pieces, even though they install it in the sense that they bring it in and they hook up the water to it. If you unhook the water, they're not allowed to unhook the water in Massachusetts. So I had to get out my wrenches, but they hook up the water to it and they bring it in, but they don't take off all the packing stuff and they don't put the shelves in. And of course we had to remove all the stuff from our old refrigerator and we had to reload it into the new refrigerator. And so we just got done, half an hour ago and went out for takeout.
Wow.
So I'm still eating my lunch.
Is that the Chelsea game that's on there?
That is the Chelsea game.
Okay. Don't tell me I got it recording. So
All right. Are we ready to go live on YouTube?
sure. We're together. We're going to be.
Don't mind the seating.
Yeah, that's fine. 'Tis the season. Wine, song, food, and fun.
Stuff like that.
Right.
Just don't let your partner find out.
Oh my goodness. Yeah. Not the season for dieting.
No. That's January-ish, maybe.
Where'd Phyllis go?
She's still upstairs.
Oh. She got a book to read or something?
Yeah.
Okay. It's a little warmer up there. The screen is not showing up. Looking into it.
We have fan mail.
Looking into it.
Is it time for the orgy?
Is that one of the holiday traditions?
Well, in Scotland, it's year round. The sun goes down, the pub's open, and we're fine.
Yeah.
Lots of little Scottish people running around.
I'm not dressed properly for an orgy. I apologize. Okay, we may be live. 15 seconds. Here we go.
All right, you're counting down. Are we all getting transferred into our room now and stuff, or
Yeah, we already are.
we already are? Okay.
Well, hello.
Hello, how are you?
I'm doing well.
Are we back?
We're back. Happy holidays.
Happy holidays. Did you enjoy your turkey day?
I did enjoy my turkey day. We had a couple of friends
Oh.
for Thanksgiving. They tasted yummy. Yeah.
Well, we were over at a friend's house and they tasted really good. Somebody made the most amazing apple pie.
Yeah, I've studied
Oh,
many recipes over the past 15 years about how, but I hope that all are pleasant, if not a great Thanksgiving holiday. And that goes for our panelists as well. We've got Ivan and Michael and John. And our friend Abby is not able to join us today. She had a prior commitment.
She's doing important stuff.
She is very important stuff for the American Humanist Association.
Oh, really?
And I just want to give a call out that we're here partially because of a grant from the American Humanist Association to support this activity. And also we thank the Prairie State Humanists that Mike and you and I are members of, and Ivan just as well be considered a member. He's in the Chicago area. And then John
And
is
Mike?
out. And yeah, Mike. And then John is out on the East Coast. So
And our cat has joined us,
excellent.
our science cat.
So speaking of science, that's a wonderful segue.
Isn't it?
Yeah, we're here for Sidewalk Science. And if you've missed some of our previous programs, they're up on the YouTube channel that I presume you're all watching right now. So you can find some of those. You know, this is like our 6th program or so. So we're still occasionally working out some technical glitches. Look at some of the prior programs. I think the most recent one starts in the middle of a conversation due to a sound issue. Our technical guys will ask me a question here. And he says we have 5 guests watching this already.
All right.
You had a whole list of things that you
I
thought were.
did, and I ran out of the house without them.
Oh no! Well, do you remember like one of them to get us started?
Well, I remember a discussion you and I were having. There was an article which you brought to my attention that life on Earth, intelligent life on Earth, is unique. That is, within the universe, there is such a small probability of intelligent life anywhere else that we must consider ourselves to be unique. We've had
That's what the article presented.
That's what the article
or
said.
Concluded. Yeah.
Of course, this opens up a huge can of worms.
Maybe the worms aren't unique. Maybe humans are unique, but worms are not. How about that?
There you go.
Well, this was the case for intelligent life versus life in general. It conceded that bacteria-like animals or virus-like critters could exist, and that's not a problem. The problem was, could they rise to the level of intelligence, such as ourselves? If we consider ourselves intelligent, that is. My contention, of course, was that it's hooey.
What's hooey? The intelligence?
That the idea that intelligent life is not going to arise reminds me very much of the religious points of view, saying, well, it's just too complicated. It's just too complicated, and it couldn't possibly arise. And so you get Michael Beebe in there and all those other groups, and the creationist argument that of complexity, to which I say, given the chemistry of the universe, given water, given time, it's inevitable. So what's you guys' thoughts?
Well,
Yeah, go ahead.
Okay. Can I come? Yeah. So, yeah, I also believe, but it's an act of faith, really, that it is inevitable that life is abundant in the universe. If you talk about life at some level, which could be the sort of level of single-celled life or a bacteria or so on and so forth. When it comes to intelligence, there, I would say, well, first define intelligence. I mean, is a dog intelligent, a bird intelligent? I would say, yes, they are at some level. And it's not a yes, no thing. You're either intelligent or you're not. It's sort of a continuum. Okay, that's what I think. Now, when it comes to advanced like civilizations or people, who actually have a scientific, or beings who have a sort of scientific thing, I think it depends so much on the longevity of such civilizations, because, we've only been in 13.5 billion years, we've only been capable of technology and science in the last, tiny, tiny fractions. So, a year.
Yeah.
So, and maybe it's not going to last very long if we don't put ourselves together. It may be only lasting for a few thousand years, and then we won't any longer be a technological civilization. We won't be using radio and so on. So these arguments about SETI, searching for intelligent life, meaning searches for life that would actually communicate and use radio or other, electromagnetic waves to communicate, that may be a very brief phase of any existence. And then that, of course, in this Drake equation, the longevity of a civilization is a key part of it. So my personal feeling is that although I believe life at some level is probably common throughout our galaxy, life at the level of using technology, maybe we are unique in our galaxy. Maybe I don't
During
know.
this epoch.
The inference, I think this is about the paper that did a Bayesian analysis, right?
Right.
Yeah.
Get your
Yeah.
opinion on that.
Yeah.
Go ahead.
So it's based on, there are a couple of key features that they assume are required for intelligence. One was the eukaryotic revolution. So you could have multi-celled life forms. That sounds pretty reasonable.
Could you, Ivan, could you tell our viewers what eukaryotic life forms mean?
Now I wish Abby was here. Eukaryotic means so eukaryotic cells are more complex than prokaryotic cells. They develop
There you
later,
go.
and they have internal structures that look as if in their evolutionary history they absorbed other single-celled life and created a sort of symbiotic system out of it. And these cells have it's the eukaryotic cells which are able to form multicellular organisms like plants and animals. Now on Earth,
As opposed to like bacteria that don't do that,
right,
and
right.
have been around far longer. Actually.
Right, and there are eukaryotic bacteria. Bacteria, I believe, are eukaryotic, right?
I don't think so. I think it's bacteria, archaea, and then eukaryotes. But in any case, bacteria and archaea are relatively primitive single-celled organisms compared to eukaryotes, which eukaryote means true nucleus, true nugget. And so there are different theories that the nucleus, the mitochondria, the chloroplasts in green plants, many of these relatively more complicated features of a eukaryotic cell were acquired over the course of time by fortuitous symbiotic events where one bacteria or prokaryote ate another, or archaea, I should say, ate another.
But they became a
Right.
symbiote.
Right.
Right.
So,
So-
in any case, go ahead.
Yeah, so in Earth's history, very soon after the Earth's surface had cooled, we got prokaryotic life. It formed so quickly that NASA is looking on other planets to find this kind of life because they think it would form so easily. But eukaryotic life took, I believe, something like 1 billion years beyond that to form. So
Can I interrupt? Just
Yeah.
ask for clarification. So these are long words, right? For a visitor, long words. Isn't it distinction of single cell and multi-cell? When single cell life lasts for 1 billion years or so, and only when 2 or more cells got together and that things took off, and that's really the distinction: single cell or multi-cell. Is that right?
Yeah. yes. So it took a
There are
billion years.
single-celled eukaryotic life forms, like amoeba. Amoeba are single-celled eukaryotes.
And my favorite, the rotifer.
Rotifers, right?
Mhm.
So there are single-celled life forms that are, quote, complicated cells, eukaryotic cells.
I'm a
But
bread baker.
all-
My favorite is yeast.
Right, there you go.
Ah, yeah. Oh, yeast.
But every form of multicellular life is comprised of eukaryotic cells, whether it's a colony like a slime mold, or a flea, or an elephant, or a human being. All multicellular life other than just simple colonies of, you know, critters that live together. All complicated life forms are eukaryotic. They're comprised of more than one, typically specialized eukaryotic cell.
Then there was another milestone, which is sexual reproduction also took a considerable amount of time. So, so it means that late after this solar system formed, you ended up, it took a long time to go from prokaryotic single cell life into life that could create multicellular life forms. And then the next question is, well, how much time is left for how much longer will Earth be habitable, right? So
that's all part of the Bayesian formula.
Right, all part of the analysis of how frequently should we expect to find multicellular advanced life on various planets. Let's say just animals. Even if let's not think about intelligence. I guess you could say intelligence took what, 500 million years?
Well, it all depends. If you look at the paleontologist point of view, and we look at some of the theropods, especially the later theropods, they were developing very, very rapidly in their mental capacities. They were
dinosaurs, theropods.
Yeah,
Okay.
the raptors.
Yeah.
And so again, the two-legged, very quick, but they were going together as groups. They were developing very, very large brain cases, and they were like birds. They had an extended brain coming down their spines. And we look at it, we say, had they given another 500 million years, would they have been intelligent? They had the fingers, they had all the tools, if they just had a larger brain. And then we look, for instance, at the differentiation between human brain and chimpanzee brain, and we see it's one gene. And if you take that gene and you put it in a rat, the rat's brain suddenly goes 50% bigger. And so the small changes it takes to go from a lizard to an intelligent being, once you've got to the size of a large multicellular animal, seems to be relatively slow to me. And given time, just give it 1 billion years, give it 2 billion, give it 3 billion. What the heck? What's a billion years between friends? As long as your sun is going to last 15 billion years, and your planet is going to last 5, 6, 10 billion years, it's time.
Yeah, but civilization or intelligence, maybe not. Would any of you care to define intelligence? What you mean by that?
No, but let me dispute what Joanne has been saying a little bit. It took 3 billion years or so between the emergence of the first bacterium and the first bilaterian, the first bilateral organism. And then it took another 500 million to get to the big brain theropods. And then it only took 100 million to get to us. So the big brains are a phenomenon of very recent evolution and not a phenomenon of the long term. And then you have to look at stellar evolution, because the sun continues to get more luminous. And it is currently we're seeing people making models of Venus, where Venus very early in its history had oceans. And now it's this extremely hot, completely inhospitable place. And what made the difference is that with stellar evolution, the sun became more luminous and made Venus hotter. And so it lost its oceans. Part of the problem is that Venus doesn't have a magnetic field, so it loses water faster than the Earth does. And that's something that we see also. How long will the Earth remain habitable? Well, the estimates I've seen are about 1 billion years. They're not long compared to the history of life on Earth already. We're nearing the end chapters.
Yeah, yes, a billion years, 1,000 million years in the future. I mean, do any of us think that humanity will survive for anything like, a million, let alone a billion, or even 100,000 years in the future? But okay, that's humanity. That's not talking about intelligent life, because there's plenty of other intelligent life on Earth that is non-human. Like, I think the birds are pretty intelligent, some of them, and dolphins and so on. There's a lot of intelligence around. Maybe humanity will become extinct. Maybe we'll kill ourselves. Okay, that's certainly a possibility. Or big major changes. So,
Oh, I'd agree completely that we develop intelligent life, and the likelihood is that that intelligent life will then destroy itself, just like we're doing right now.
So I have a
Yeah,
thought that is sort of about this, because I mean, if you look at how our modern civilization arose, it was helped enormously by using fossil fuels, by using coal and oil and gas to make the industrial revolution and so on and so forth. Now, use of fossil fuels is a very time-limited thing. I mean, we cannot continue to use them. So, okay, we have to get rid of that fossil fuels, but it could be that almost any advanced civilization will go through a phase where it's having to use some limited resource like that in order to become a technological civilization. Okay, and then it's going to change. So I think I can guarantee that in a few hundred years we will not be reliant on fossil fuels anymore, and maybe we'll be living in a different way. We will not be living the way we are now, driving around cars and flying planes and so on. It's going to be different. Hopefully, civilization can survive for a long time, but I still doubt that will survive for 100,000 years actually.
Yeah, John, I believe asked the question about can we define intelligence. I'm gonna punt on that question, and instead I'm going to refer to the fact that we need to be a technological species. And in my opinion, the hallmark of a technological species is the ability to create artifacts, and we might call that technology. That's a synonym for it. But anything from pointed spears to satellite dishes and whatnot, which we will talk about in a moment, by the way. I think the ability to manipulate your environment and create artifacts deliberately from your environment, in not just a rudimentary way, found object like a stone or a stick. I think that is a hallmark of the sorts of intelligence we're talking about when we're speculating about space travel and communication.
But we know, for instance, that chimpanzees and bonobos create tools. They break rocks, they break off sticks and reform them and everything else. So do crows. So where is that? I mean, do they make artifacts? Well, in that definition, they sure do. Therefore, they're intelligent. Well, I'd actually sort of grant that.
Yeah. Well, I'm trying to draw a line between just being smart, which a dolphin could be smart, but they don't have access to fire.
You have a smart dog.
Right. They don't have access to fire underwater. And so there's speculations about what it would mean for an intelligent, highly sophisticated population to arise on a planet where they've got art and culture and some kind of literary tradition, but because they're aquatic, they would not be able necessarily to develop high technology artifacts because they can't smelt iron and do some of these other things that require an atmosphere.
Whereas Neanderthal and the earlier humans were very good at it. We go down to South Africa and we find 2.5, 3 million years ago, there were people-like things, growing on caves, burying their dead, doing all these other important things that are prerequisites of society.
Whenever we talk about the Drake equation, which I think Mike and John mentioned, whenever we talk about the Drake equation, one of the corollaries of any proposed solution to that equation, which is sort of a hand-wavy attempt to define the probability of intelligent life at any point in time
We're good at it.
in a particular region. And there's factors like the probability of life arising, the probability of complicated multicellular life arising, probability of intelligence, probability of technology, the longevity of that technological species. So different factors in the equation. But what we see when we look around ourselves in the universe is we don't see any obvious evidence of a spacefaring galactic civilization. And so there's this idea that goes along with the Drake equation called the Great Filter. And the notion there is that one of the reasons we don't see obvious signs of an intergalactic civilization is that it could be that there is a great filter that prevents many civilizations from becoming technologically advanced, whether that's self-destruction, whether it's the jump from prokaryotic to eukaryotic cells that was so important for the development of complex life on Earth, or whether maybe it's just space flight itself, just the challenges.
Yeah, we've discussed space flight here,
Right.
and sort of laughed and giggled as the universe is expanding. How do you achieve a speed of more than 140,000 light kilometers per second just to travel one direction because it's doing this?
Yeah.
So it's a complex.
Yeah.
Go ahead.
Yeah.
Mike.
I mean, you use the word at one way. You want to draw a line. When we talk about intelligence, Scott, I think we should start thinking about drawing a line in a sense, because these things are not digital yes, no, 1, 0. They're continuous, right? So, I think a bird has got some sort of intelligence, etc., but I can't define it. It's just a continuum. When it comes to something like SETI, okay, which is listening to see if it can find signals from a intelligent technological civilization, within 100 light years or 1,000 light years or whatever.
Just say what SETI stands for.
Oh, search for extraterrestrial intelligence. And it started out by saying, look, if there's a civilization using technology like our Earth within 10 or 100 light years, we may be able to hear their radio transmissions, or they may be targeting us. So it's been a big program, and it's quite well funded, actually. And it's an interesting thing, but the probability, even if there are technologically advanced civilizations in our galaxy, of having one within 100 or 1,000 light years, which is a tiny, tiny fraction of the galaxy, is very, very small. But when it comes to now talk about have they visited us, the UFO, I mean, I believe in UFOs. That stands for unidentified flying objects. And there are plenty of objects that we've seen flying but haven't identified. So they're UFOs, in my opinion. Are they visitors from another planet? That's a totally different question. And, when you think of the distances involved, I think that maybe God has invented social distancing by keeping us so far apart that we can't visit each other, right? Because
Well, I think it's true that the difference between traveling from the Earth to the moon and from then going on to the nearest non-solar star is that difference is that next jump is far greater than the jump between walking across the street and going to the moon.
Yeah.
So I think interstellar travel is extraordinarily difficult.
Yeah, I agree.
And I wonder if any civilization that had achieved sufficient mastery of matter and energy to even attempt it wouldn't find better uses of that mastery than that. But the other thing, let me say, as someone who is actually an exoplanet researcher, strangely enough, I never expected to be that, is that we're finding that, one of the terms of the Drake equation is common. We're finding that planets are very common in our galaxy. On the other hand, planetary systems that resemble the solar system seem to be odd. And in particular, the solar system lacks the most common kind of planet, which is planets with masses between the Earth and Neptune. And that's an odd feature of the solar system. And then we get to the Earth, and it seems to have this very odd feature of a very large moon, which seems to, we have good ideas of how it happened, how we got that moon in terms of collisions with another body, but that doesn't seem to be a very likely thing to happen in the history of a planetary system. And then the other thing I look at is the second most common molecule in the entire universe is water. The first is hydrogen, is molecular hydrogen. And so I would expect that any planet that has the capability to retain water would have a lot of water. And that's kind of what we see. Titan has lots of water. It's just a rock rather than oceans. But in the solar system, we have 3 planets that are incapable of retaining their water, and so they've lost it. And then we have this one peculiar thing that we live on that has had just enough water, very little compared to cosmic abundance, but just enough water that it's got a thin coating on the outside that only partly covers it. And it's had that for billions of years. And I think my guess is that that's a very unusual situation. But I also guess that that had a lot to do with the evolution of complex life.
Yeah, certainly terrestrial life, like I was mentioning earlier about hypothetical poetic dolphins or poetic squid on some other planet. But because they live in an aqueous environment, they would be to everything we've been able to successfully imagine heretofore, be almost impossible for them to develop high technology, electronics and forged metals and high-speed transportation and whatnot.
And there's this interesting.
I follow your argument. I agree with that. But when you say very unlikely, if it's 1 in a million for a planet, that still leaves about 100,000 planets
Right.
in a galaxy.
Right, that's your argument, right? That
Yeah,
this is-
but who says it's not 1 in a trillion?
Well, okay, but
We don't
But still,
know.
we got a universe.
even if it's only 1 in a million chance, and there's 100,000 in our galaxy, the chance any of them are within 1,000 light years is very small.
Oh yeah.
Even traveling 1 light year is almost impossible for anything, right? I mean, the fastest things we've ever sent out in space, Pioneer and Voyager spacecraft, right? And they're going out there, speeding away at 1,000 miles a second or whatever it is, but it's still going to take them 100,000 years to get anywhere near the nearest star if they were pointed at it, which they're not. Okay, but and there is a thing called the speed of light, which is an absolute limit on matter, and this is a site, so. Putting aside wormholes through space-time and so on, nothing can get to the speed of light that's got mass, and I include people and spaceships and so on. And the amount of energy it would take to get even half the speed of light for a spacecraft as small as a mini car or something like that is more energy required than you can produce in all the power stations on Earth for a year. I mean, it's just out of the question to even get within half the speed of light or anything like that. I mean, so, and that is such solid science that, it's relativity, which is so well tested. We try and get our protons up to the speed of light in a Large Hadron Collider. We can get up to 99.9999 the speed of light with them, but you can't get up to the speed of light because it takes an infinite amount of energy, according to Einstein, and he's right. Okay, that.
So why can you do that with a proton, but you can't do it with a automobile?
Well, because
what's the key?
Automobile weighs about 100 trillion times more massive, and that takes 100 trillion times more energy. You see, because a proton is, there's about 10 to the 24. That's 1 trillion protons in a gram. Okay, so in a kilogram, you've got 10 to the 27, which is 1,000 trillion protons. And a car is 100 kilograms or whatever it is. I mean, and that's the energy you need. So, and you
You
know,
can't just put a car in the into the LHC and accelerate it to the speed of light.
It's really small,
Yeah.
a really small one.
we put a bunch of protons in there, and there's circulating in the LHC is about, you know, maybe 100 trillion protons circulating, but that is a thousandth of a microgram. Okay, it's
Wow.
still a very small amount in mass, and you know, it takes a lot of energy to get them up to that energy.
Is that rest mass or mass?
Oh my goodness.
Oh, here we go.
Because they're
Now-
very different in the
Yeah.
LHC.
Right. Proton
Yeah.
at rest weighs about 1 GeV of mass.
Yeah.
Right. And in the LHC, they're 14,000 GeV. So nearly all their energy is kinetic energy, but it's all the same. It's all the same. Einstein said that, right?
I wanted to come back to you. Did you have additional thoughts about that paper that talked about a Bayesian probability of complex or intelligent life? Did you have additional thoughts about that?
I didn't check their numbers, but I mean, just the thing that I was not aware of is that we only have 1 billion years left. I know it's depressing, a depressing thought, right, John? But
Yeah.
I'm not going to
Yeah.
make it anyway. So
so yeah, so I mean, it just shows you that so much of the available history for life on Earth has already been taken up just by getting to multicellular life forms. And so, all things being equal, if we thought that the Earth was typical, that tells us a lot about what we can expect on other planets. Like, you know, for the formula to be wrong, you basically have to say that there's something very odd that happened in Earth's history that prevented complex life from forming for 1 billion years. And you know, for all we know, you know, if you have an entire planet like a test tube, the size of an entire planet, and it still takes 1 billion years for that test tube to develop multicellular life, it must be very difficult, a very difficult thing to evolve.
Yeah, but Ivan, don't get depressed. I'll cheer you up. You know, in 1 billion years, or even 1 million, we'll probably, if we don't kill ourselves, be having like out on Mars, which has got an extra time to live, or satellites of Jupiter and Saturn. We can, on the long term, if we do pay attention to ourselves, move out in the solar system. I'm not saying out to distant stars. I'm not saying that at all. That's happening.
Yeah, that brings up a couple of points that that have come to mind as you all have been talking. One is, John, related to what you said earlier about exploring exoplanets. Are there mechanisms that are being developed from a practical, real technology science standpoint to probe the composition of other worlds, to see if there are water worlds or worlds with dry land or anything like that? You know anything about the technology being developed in that
yes,
regard?
yes, there are a couple ways to do that. One is that when an exoplanet passes between its star and us, some of the starlight shines through the atmosphere of the exoplanet. And it is possible, and with some of the larger exoplanets has even been done with existing instruments, it is possible to look at the absorption spectroscopy of the atmosphere using the very tiny changes in the starlight when the planet passes across the star. And there is a brand new mission called Cheops, which is just now coming online, which is designed to do this kind of work. And the James Webb Space Telescope is supposed to do this also. Similarly, another way to do it is to use reflection spectroscopy. And there you use the fact that when the planet is on the far side of its star from us, it's illuminated by the star. And then if it goes behind the star, all of a sudden we don't see the planet anymore. There's a very tiny dip of, it's even smaller than the dip in light that's due to the transit. But then you can again look at reflection spectroscopy based on the change when the planet goes behind the star and disappears and then reemerges illuminated again.
Are you looking at this? Are you zooming in, so to speak, on the planet, or are you looking at the spectral signature of the entire system?
You're looking at the spectral system and the spectral signature of the entire system. What you see is you see the spectrum of the star, and then you see the planet modifying it as a time fluctuation. And so you try to chew on that time fluctuation in the spectrum to get the spectrum of the planet.
John,
Excellent.
I'm wondering if the simple experiment has been done of, during a total eclipse of the moon, to have a detector on the moon that looks at the Earth's atmosphere and analyzes it spectroscopically to prove that we can do that.
They'd have.
It's not been done with anything on the moon, but it has been done with an Earth observation satellite out at the outer Lagrange point.
Wasn't it also done with moon with Earthshine? So you can
Yes,
see
maybe yes. The
Earthshine
technique,
destroys
yes.
the spectral lines, I suppose. But what about a transit of Mercury or transit of Venus? We must have done that, no?
Yes, well, Mercury is boring because it doesn't have an atmosphere.
Okay, none at all, really?
It's a rock.
It doesn't have any atmosphere, Mercury?
Well, it has some, but not enough to produce an absorption spectrum. Now, Venus, yeah, I don't know what's been done with Venus. Transits of Venus do happen. I'm not aware. Probably somebody has done that. They're not very common.
Right.
They were a very big deal in the 18th century.
I think
They allowed us to calibrate the size of the photosystem, didn't they?
They did. And a couple of guys named Mason and Dixon forged a partnership back doing that job.
Okay.
Bit of American history.
Mike, you're muted.
Sorry, the first time we will have evidence that life is on another planet probably is through this measuring the atmospheric composition by absorption in these transits, right? So
That's correct. Although what will happen, because we already know from what's happened with Mars and even lately Venus, although that phosphine result seems to have disappeared. When we see exotic chemistry on Mars, the first thing is, oh, well, that matches what we expected from life. And then somebody comes up with some inorganic explanation. And, you know, the jury is still out, and it's going to be even harder to figure it out for exoplanets.
yeah, but didn't the atmosphere of Earth, it's very odd, isn't it? It's got so much oxygen. Wasn't it formed somehow by early life?
yes.
Well, that's the thought. But on the other hand, it's not entirely clear that an oxygen-rich atmosphere couldn't be produced by some other mechanism. We, you know, after all we see is the solar system, where we only have a few atmospheres to study.
Yeah. So one of the things I've heard is that on a water world, the water vapor could reach heights in the atmosphere where the water molecules are photodisassociated. So the hydrogen is broken off of the oxygen. And if it's a water world and you don't have surface rocks and other handy materials to support oxidation, that can grab oxygen out of the atmosphere, then you may be able to get a buildup of oxygen in the atmosphere of a water world without without life.
Once you get to the hydroxyl, it's going to be very, very difficult to go beyond hydroxyl. You can strip one hydrogen, but then you've got hydroxyl, and hydroxyl exists in space. It's a wonderfully stable ion. So I don't see that breaking down to the oxygen molecule itself. That takes a little more chemistry.
Well, except that we see atomic oxygen,
Takes
a lot of
ultraviolet.
atomic oxygen in the exosphere. In fact, it's a big problem for people like me because it eats away on optical filters.
I'll make a note of the fact that oxygen is a problem for John.
It is a problem for me.
You need it, but not too much, right? We all need it.
Well, yeah, well, it's actually one of the more toxic substances in our environment. If you were to breathe twice as much oxygen as you normally do 24/7, you would become seriously ill.
Okay. Any other topic, John, Scott? You want to direct us?
We're having really intermittent network. I wanted to talk about Arecibo. I wanted to talk about Arecibo and its demise and whatnot. But we're having some network issues down here. I'm going to disconnect and reconnect my computer, so we'll be back. Joanne and I will be back in just a moment.
Bye.
Okay.
Temporarily.
See you soon. Bye.
Sayonara.
So in one of the links that Joanne circulated was about simulations of the solar system, and suggested that there was a planet between Saturn and Uranus. And that, of course, it's difficult to just look at our solar system today and find evidence of that, because it would have happened long ago, and the current orbits look stable. But what they did is they ran a bunch of simulations of solar systems to find out how you can get a solar system that looks like ours does, with the rocky planets exclusively in close orbits. And they find a pattern where you could have a planet ejected from the solar system, resulting in a solar system that looks the way ours does. And this is evidence from simulation. It's not direct evidence that such a planet actually existed, but it may be another piece of evidence that our solar system is very unusual, that Earth's position, its magnetic field, having a moon, and now perhaps having a solar system history that's unusual, might make us even weirder.
Yeah. Of course, any particular configuration is infinitely unlikely. Right, any particular one.
That's
but
true.
John, Ivan, there's this odd thing about Bode's law that had it was a pattern of planetary orbits that said there should be one between Mars and Jupiter, and actually there was one, but it completely broke up and made the asteroid belt. Okay. Now I think that Bode's law was just a sort of arithmetical thing, but nevertheless, we do have this asteroid belt between Mars and Jupiter. And is it not accepted that there was a planet there that broke up?
The idea is that there were multiple bodies there that were still dwarf planets, and that some of them have collided and been disrupted. But the other thing is that the current prevailing hypothesis, which basically stands because nothing else does, for the origin of the moon, is that it was the collision of a Mars-sized body with the Earth that ejected a large amount of lithospheric material from the combined body from the collision, because the moon has lithosphere that looks very similar to Earth, but it has a very different density. So it apparently doesn't have much of a core, because a lot of the mass of the Earth is in iron deep beneath our feet. So the thought is, the belief is that the moon was ejecta from this collision. So if this hypothesis is correct, and again, there doesn't really seem to be a good competitor to it, there were more planets kicking around in the solar system than we know about now, because that body had much more mass in it than the asteroid belt does.
Yeah.
So yeah. Now here's another thing. So planets all spinning on their axes, right? I mean, okay. Uranus has the extreme axis, which is more than 90 degrees out of whack with the orbital angular momentum, right?
Yep.
So something happened to do that, right? Something.
It's going backwards.
It must have been some sort of a collision with another body or something that kicked its angular momentum. Angular momentum's conserved, right? So it must have had something. That must be something in the past that kicked it, right?
And
it's going
the thing is that we look at exoplanet systems, and our planetary system looks relatively tame. A lot of the exoplanet systems have planets that look like they've interacted in the past, and they're at all different inclinations, and they look much more complicated than ours. We see hot Jupiters, which we don't think could possibly have formed in their close orbits, in the close orbits they're in now, but somehow must have migrated in toward their stars.
Well, a hot Jupiter
we have a selection bias because we're easily seeing the big ones, but not the small ones, right? So if
that's true. It is easier to find the hot Jupiters than anything else. But the thing that's odd is that we didn't expect to find any at all, because we didn't expect that they could be formed there.
Yeah, a hot Jupiter, for our viewers, is a planet about the same size or bigger than Jupiter, but orbiting close enough to its star that it's as hot as Mercury or hotter. Some of these hot Jupiters orbit closer to their stars than Mercury orbits our star,
which is insane.
Yeah.
But I think our solar system would not be detectable right now with these techniques unless it was really quite close. Is that correct?
Yes. The TESS, which I'm involved in, is designed to find things like our solar system around nearby stars. And we are finding a few Earth-sized planets, yes.
So I have, John, another question for you as expert in this field. So one of the ways we find planets around exoplanets is because the star wobbles in response to the gravitational force of the orbit of the planet.
Yes.
Right? So take that to our solar system. The sun is actually wobbling because of the influence of Mercury, Venus, Jupiter, Earth, blah, blah, blah. So have we actually done the measurement of measuring the sun's wobble and analyzing it and discovering the structure of our solar system from the sun's wobble? Have we done that?
I don't think that is currently possible with present. Yeah, I don't. Perhaps you could find Jupiter. I don't think that's currently possible with current technology. The systems that we study using that technique tend to involve smaller, lighter stars than the sun, and planets that are closer into their stars, so that the velocity of the wobble is larger. Because the way it's done is to measure the velocity, not to measure the displacement of the star. So if you have a planet in a close orbit and it's going around very fast, the wobble involves more velocity than if the same planet were farther out. You'd still have the star moving back and forth the same amount, but not so fast, because the orbit period is longer.
Yeah, but I understand that the wobble we can detect now on stars is of order tens of meters per second. I mean,
that's right.
It's very small. So it'd be a very interesting exercise for a PhD student to analyze the wobble of the sun and conclude on what the planet. because each planet's got its own orbit path year, right? So you can, you know that to start with, but it'd be nice to derive it from the sun lines, spectral lines measured very precisely. Maybe it's not possible. I don't know. Well, it's certainly possible, but whether it's possible now, I don't know.
Yeah, the sun is annoying to study because it's so bright.
So you're annoyed. You're
Our-
annoyed by the oxygen in our atmosphere, and you're annoyed by the fact that our sun is so bright.
It's really
Yeah,
cool.
well, you point a telescope at the sun and the telescope melts. That's
Yeah, he doesn't point any of his telescopes at the sun. None
No,
of them.
All right. So we have a question from Peter on YouTube asking why the prospective vaccines for COVID need to be kept so cold. And I'm currently reading through an article on the internet that seeks to answer that. But without having finished this article, I think it's probably because heat, one of the things heat does to molecules and RNA, which are in some of these retroviruses, RNA is just a big molecule, is heat causes them to jiggle. And if you get a molecule jiggling too fast, pieces can fly off of it and it can break apart. So in
It's
fact,
even closer because this is mRNA, which is a much smaller molecule.
yeah, messenger RNA.
Yeah.
So it's just like a little snippet of RNA. And I do see in this article I'm reading that is what they're talking about, that any kind of temperature, any significant temperature approaching room temperature, the vibrations in those little fragments of RNA become so significant that they disintegrate.
Which is a huge advantage
Yeah,
of the
but
Moderna
our
virus.
bodies are full of RNA and mRNA and so on, and we're at room temperature or body temperature. So this must be a very fragile molecule,
Yes.
very fragile one, right, in this virus.
Yeah, this is a big advantage of the Moderna over the Pfizer. Pfizer has to be really, really cold, whereas the Moderna, yeah, but it's only carbon dioxide, so we can easily work with CO2.
The liquid nitrogen is not so hard either, is it? I mean, you can do that in a dewar and fly stuff. And
But in a smaller community, I mean, in Chicago or New York, where they've got these huge facilities, that wouldn't be a problem. But you get out to Lombard, Illinois, and what do we have? You know? So, and then you get out into the distant areas of the Dakotas or Wyoming. They're destitute in terms of this kind of technological apparatus.
So
But then, I mean, you can make a dewar that keeps stuff cold, you know, because it's a vacuum flask and so on and so forth. And I mean, maybe we should invest in making big dewars that can take hundreds of liters of
Well,
one.
there's a huge.
Well, we
industry out-
usually drag liquid nitrogen around in 160-liter dewars. And
Yeah, yeah.
you know,
There's a
the
huge
folks at
industry out there
MIT
now.
I work with have so many of them around that the safety office has to have oxygen sensors around to make sure that it doesn't boil off so fast that it asphyxiates people. So in certain environments, liquid nitrogen is an extremely common substance, but out in the boondocks, not so much.
So there's a big company, several big companies now that are building these extreme refrigerators and selling them for a handsome profit, but they're rolling them out and they're coming out on the 747s and going throughout the world.
So as a physicist about absolute cold, my thinking is this: if you know, we make milli-degrees Kelvin in the lab above absolute zero, even a degree above absolute zero doesn't come naturally. That means to say that something of a degree above absolute zero, or 2 degrees, liquid helium, right, is only possible when you have a technological society. This comes back to our previous thing. So if we are the only technological society in the galaxy, we have the coldest place in the galaxy in the Large Hadron Collider or in other cold places, because we can make stuff, because we're sitting in a bath of nearly 3 degrees above absolute. That's the microwave background, and nothing natural can be colder than that. So a rock in space is at like 3 degrees absolute. It's sitting in the bath of the microwave background, and there's nothing colder than that natural. Okay, so that's an interesting thought.
So Peter also had a second question about human evolution. He was wondering about the difference between an evolution, I'm going to paraphrase it a bit, sort of a gradual evolution from pre-existing entities versus an evolution in kind, and kind of a jump to humans. And I can say that from what I've read over the years about evolution, there is no evidence that any attribute of a human being, including our intelligence, has been generated as a completely novel invention by evolution. We go back to the idea, I think several of you were talking about this earlier, that biology especially is a continuum. It's really problematic to draw lines between intelligent and not intelligent, as we were talking about earlier. And Joanne, you pointed out that chimpanzees have, what is it, 98.9% or something like that,
really close,
of
really
the
close.
same genetic recipe.
And
that we
bonobo
have.
is even closer.
Thank you. Yeah. So, for example, one of the things that seems implicated in human intelligence is exactly what you mentioned, a particular gene that seems to leave during development, your body is growing and adding new cells to developing organs like kidneys and spleens and brains and whatnot. And there's one gene that seems to be a little different in a human that leaves the add new cells to the brain program of the recipe, leaves that part active longer than in any other animal. And so our brains tend to accumulate new cells during our prenatal development more rapidly and in more quantity than anything else, just because of this slight change in our recipe. So I don't think that there's any evidence that I've seen that shows that human evolution involves a change in sort of the kind, in the overall gross characteristics of biology.
And yet there are drifts, and we can see drifts. Now, this is the different from evolution. This is saying that some people are different from other people, but is there a biological or other kind of a necessity that says this group of people will not survive and this group of people will? For instance, color vision. There are women, primarily in Eastern Europe, who have developed a gene in the eye to see yellow, specifically.
Yeah.
And so they have an interesting biological difference. Now, is this sufficient to change the entirety of human beings? Well, only if there's a biological advantage.
Right.
Now, if there's a biological advantage, yeah, it could. But is there one in, again, this modern technological society? Probably not. So there are many changes that could be going on within the human species, which under other circumstances might indeed be forcing us in a particular direction. But at this point, looking at us from a technological species, there's no great driving force one way or the other. We have plenty of food, we have plenty of air, we have plenty of water, we're working hard to maintain, we're doing all the things we can do to maintain status. And so real drift, yeah, there's a little bit of here and a little bit there, but a big change, I don't see it happening.
Yeah.
Right. But a yellow vision sensor might be very important to see at the canary in the coal mine, right?
Right.
Assuming we can get some photons down into the mine.
Yeah. There's a story when Fermilab started and Bob Wilson had a herd of bison in Fermilab. The story was that, he put them there to test if the radiation levels were too high, the bison would fall over like the canaries in the coal mine,
Oh my. That's not why they were there, though,
That's
right?
not why they were there.
Okay.
But they were there because he was brilliant and he saw the bison were being exterminated. And he said, we've got some land, we can have a herd of bison. And we've had one ever since. And it's great.
Wonderful. I've never seen the bison at Fermilab. I know they're there and I've been there many times, but I've never seen the bison.
I've even seen one being born. The mother, we watched, and the mother was standing there and the baby calf popped out. So they're not always, you can't go in now because you can't be allowed on site now. I can't be allowed
Yeah.
on site now. Okay, but without special permission. But,
Well, after COVID, Mike, you should take us on a bison tour.
yeah, I can do that when it opened up again to
Yeah.
visitors.
And we keep going, please reopen. That
Yeah.
was one of our favorites. We were there all the time.
Yeah, we love going to Fermilab for the various science lectures. There's another question on YouTube that came to us about what we were talking about earlier with regards to the Fermi paradox and life on other planets. The question is there a possibility that there could be planets in other galaxies, or maybe perhaps even planets in our galaxy, that have even a better Goldilocks position for the evolution of life and intelligence than Earth? And maybe these could have evolved intelligent life, complicated life, sooner than ours. It's been what, nearly 14 billion years since the universe started, and
And 5 for us.
yeah, it's been only about 100,000 years that our species has been around, give or take. Again, it's hard to draw these lines. So the question is it possible that, can we imagine a planet that would have even a more accommodating sort of Goldilocks position related to the evolution of life and intelligence?
I
Well,
would say it's actually certain, almost, no, not certain, but very likely. If there are many planets with life on in the galaxy, the chance that we are the most Goldilocksy, the most in that sense, is very small. It's a distribution, right? So, I mean, if there's 1,000 planets with life on, or 1,000 planets, the chance that we are on the extreme edge of the curve of being the most habitable, the most Goldilocks one, is very small.
There is an alternate hypothesis for the origin of life on Earth, which is called panspermia, where the idea is that the reason life arose on Earth almost as soon as it had cooled off enough that it was possible for life to exist is because there was in the interstellar dust the seeds of life that collisions with asteroids on other planets had ejected microbes, and those microbes had traveled across interstellar distances and had wound up on the Earth as soon at the time when the Earth was ready to receive them and grow life. And after all, if this is true, it will only take one cell. And maybe we're all descended from that one cell. And maybe the reason this happened is because there was some planet earlier in the history of our galaxy that was more favorable for the origin of life than Earth.
Yeah, and then also the Goldilocks, specifically this idea of the Goldilocks zone, which is where liquid water can exist on the surface of a planet. Our planet Earth is not smack dab in the middle.
We're on the cold side.
Right, we're on the cold side of the Goldilocks zone for our own solar system. So just that simple fact means that there's likely to be other planets that are in a more temperate location.
Well, that's what the greenhouse effect is good for. And it might be that we're defining the Goldilocks zone wrong.
Yeah.
And it might be that it should be defined farther out, because it's quite likely that planets with a stronger greenhouse effect than the Earth are pretty common.
Well, I keep looking back to 600 million years ago, when this was snowball Earth.
Right.
Yes.
So
now, taking the panspermia idea to the future, if, as it happens, we are the most advanced civilization in the galaxy, how are we going to populate the galaxy? And it's not by sending spaceships with people, but by sending out, 1 million tiny spaceships with fertilized human eggs,
Yeah,
and environment, and programming them to find likely planets and land and then populate them. You know, that's the way that we could do. And if
Well, one of the things that's of interest right now in planetary exploration is the idea that we don't want to send people to Mars because they'll contaminate Mars. And one of the arguments against that is calculations that suggest that enough material has been ejected from the Earth by cratering events that Mars already has Earth microbes on it.
Right.
Oh, we have Mars rocks, so why not?
Yeah.
Yes, and another hypothesis that's on the table is that life actually started on Mars and got sent here.
Right. Yeah, they had rivers and I don't know, oceans, but certainly rivers.
Yeah.
Yep.
And lakes long ago.
And Venus probably did too, although there's much less sign of them now.
We have another question from my YouTube viewer, it's a lead into a topic I wanted to bring up today about the Arecibo Observatory. You know, we were talking about the SETI program, the Search for Extraterrestrial Intelligence. And one of the first things that happened for that program was they used the Arecibo, the giant dish telescope that was built into a sinkhole in Puerto Rico that's been in the news lately. They used that telescope to beam a message out to I believe it's M13, called the Great Globular Cluster in Hercules. It almost looks like a swarm of bees. It's this very dense, tightly packed accumulation of stars in a sort of a ball shape that slowly orbits around our galaxy. These are called globular clusters. And they sent a radio message that, when deciphered, essentially says, "Hey, everybody, welcome to the galaxy. You know, we're here." And they beamed that back in the 70s, and it'll take at least a few thousand years for the message to get out there.
So so we're on speed dial.
Right, yeah. But in any case, the Arecibo telescope has been used as part of the SETI program. It was featured in several movies, including a movie about the SETI program, Contact, based on a novel that Carl Sagan wrote.
And James Bond.
And a James Bond movie, right. So this past week, the Arecibo Observatory has met its end after first one sort of auxiliary cable snapped.
And then the big one.
And then a big cable snapped about a month ago. And then earlier this week, I believe it was Wednesday, the remaining cables just had too much weight on them, and the whole thing, the platform, 900-ton science platform that supported a lot of the radio transmitters and receivers above the dish, that platform catastrophically collapsed. And the question is, when did human occupancy of the gondola on the Arecibo Observatory cease? I don't know for certain, but I assume it was shortly after that second cable broke about a month ago.
No idea.
But was there ever human observers in there? I mean, presumably they weren't normally sitting.
Well, technicians just coming and going.
Going in and coming and going. Yes, okay. Doing maintenance and stuff like that.
No idea.
Yeah, but there was never somebody, you know, the Arecibo telescope didn't have like an eyepiece, you know, where we have to have a person there looking through it or whatnot. It was all.
It's a radio.
Right.
It's an interesting idea that you don't have to, you can build this huge thing pointing just up. And as the Earth turns, you sweep across the whole sky, a band around the sky, you know, without having to have it steerable. Like Jodrell Bank, you know, the Jodrell Bank was the first steerable radio telescope. 1957 it went up. And Bernard Lovell got this thing built. And halfway through, he ran out of money. And he was in danger of being taken to court for overspending money that he didn't have. And then, to save his bacon, Sputnik 1 went up. And he could actually track Sputnik 1 with his thing. And it was the first place to do it. that radio telescope is still there. I was there 2 years ago.
Wow.
It's a great place. But that was
So-
57. That's a good story, actually. I mean,
Oh, thank you.
yeah.
No, note that Arecibo could, within limits, track things in the sky because that 900-ton platform had a moving
Movable.
part
Mm.
so that they could move the feed point around to wherever the object that they were looking at was focused.
So John, one of the questions, I think I might have emailed you about this previously, or maybe we had a Facebook discussion, but one of my curiosities is what kind of science have we lost with the loss of Arecibo? Is there anything that it did that nobody else can do?
We've lost, I don't know what we've completely lost. There's nanograv, which was trying to do gravitational wave detection of very long length wavelength gravitational waves using pulsar timing. And Arecibo was uniquely qualified for that. On the other hand, I'm in a bit of competition with them because my X-ray pulsar work is reaching the point that I'm working with people at Goddard Space Flight Center on, is reaching the point where we can do better in X-rays than radio can. And the reason is because in radio, you have the interstellar plasma speeding up and slowing down the radio waves. And so that in turn causes some fluctuations in pulsar timing that are not due to gravitational waves, but are due to this plasma. And that doesn't afflict X-ray measurements. NICER on the International Space Station has reached the sensitivity where it's about as good as Arecibo could do. So we need something better if we're going to continue with this work. But we're getting there. So that's a possible that's one place where it was on cutting edge, but there's a possible route forward into the future that by a different technique. It was the best thing for imaging objects in the solar system using radar. But there are other assets that the NASA's Deep Space Network can be used in that mode. The difficulty with the Deep Space Network is that the dishes aren't as big, although the radar equation goes as distance to the fourth. So making a bigger dish doesn't help you that much. But the other problem that, of course, the Deep Space Network has is that it's busy communicating with interplanetary spacecraft, and even cislunar spacecraft like TESS. So that's a problem. An advantage of the Deep Space Network is the dishes are steerable, so it can target things that Arecibo could never target.
There is a competitor telescope that recently came online in China as well, and I believe it's actually bigger than Arecibo.
Really big, yeah.
Yeah, I think it can do I think it will be able to take over the pulsar work. It's not at present capable of transmitting. It can't be used in a radar mode.
Okay.
So it can't do the imaging that Arecibo did.
Oh, cool. Thank you for that information. Also on science news, on the science news front, talking about radio astronomy, did any of you see this story from the past week or two about these orcs?
Yeah, odd radio circles.
Odd radio circles.
Blobs.
Yeah, so that if you one of the things you can do with radio telescopes is you can turn their signal into a picture, and you can draw contour lines that show where different signals of different frequencies originate, and you can do brightness and assign colors to it. So you can make a visual picture out of radio wave signals. And some astronomers have found hundreds, at least, of these things in this deep sky called odd radio circles, orcs. And nobody has the faintest idea what causes them. We don't even know yet whether they're in our own galaxy, maybe around emitted by a star or a cloud of dust, or whether they're associated with distant galaxies and are gigantically large.
It's a blobby thing.
It is a blobby radio blob, a blobby blob
There.
out in space, and we don't know much about them yet. Orcs, odd radio circles.
I'm sorry, Joanne, I don't know what they are.
So I think everyone is equally stumped,
Yes, yeah.
and we're all going, huh?
So there still are unanswered questions in science, and this is one of the reasons I wanted to bring that up is to talk about, we spend a lot of time on this program. Oh, there's the odd radio circle. Somebody
Yeah, I just picked it up from Joanne's email. Here's a picture of the ghostly Orc 1 blue-green fuzz on a backdrop of galaxies at optical wavelengths. There's an orange galaxy at the center of the Orc, but we don't know whether it's part of the Orc. I thought orcs were things like whales that swim in the sea, right? Anyway, we found them in the space, orcs in space.
Yep. There's a thingy out there that we have no idea what it is, but there it is.
Yeah, and I think in this article they say they've discovered many of them.
Several.
It's not just one.
Hmm.
But this is a good example of how occasionally we'll hear people talking about the idea that science is done. Maybe even physics or astrophysics is done.
This was labeled by Anna as WTF ?
The
Yes.
WTF orc.
What?
What the fuzz?
So that subheader there, are they throats of wormholes? And there's a famous principle, right? That in a headline, if there's a question, the answer is always no.
Yeah. Yeah. I once gave a seminar called "Have we found the lightest scalar glue ball?" And I was told that the answer is always going to be no. So
So science, continues. It's not just, we've talked about on this program, not today, but previously on episodes, we've talked about new human organs that have been discovered. John, you've certainly talked about some new discoveries related to astrophysics. We've got these orcs. Mike, you're involved in the search for new physics with regards to particle physics and neutrinos. And my personal inclination is to say that we're not finished. We don't know how far away the horizon is in terms of having a complete picture of all the things that are possible in nature. Even from a fundamental standpoint.
And say we're just starting, really. All the stuff we know about atoms and the particles we know only contributes about 5% of the stuff in the universe. There's 5 times more dark matter out there. We don't know what that is. We know it's got gravity, but we don't know much about it. And we may find those particles or we may not, but then there's dark energy we don't know. Now, dark matter probably is not one particle. It's probably a whole spectrum of particles. And so, we really are so ignorant, but, the frontiers of science expand and the questions expand and you never get to the end, maybe, but...
With my apologies, Mike, I think that some of the angst about the end of physics is really about angst about the ends of synchrotrons.
Yes. Yes.
I just want to clarify one thing. Is you often hear like, oh, we only know, about 5% of the universe. But we only know 5% of the universe by weight.
Yeah.
True.
Maths, you're quite right.
We don't. It's true. There are still mysteries. There are still some very exciting things to find out. But we also know quite a lot that's not likely to change.
And we know some things about dark matter that tell us that lead us to the conclusion that it's boring stuff. We have enough evidence. There's a thing called the cold dark matter theory of the Big Bang and cosmology. And the reason they use the term cold when they say dark matter is because the notion is that matter, whatever it is, dark matter, does not interact with itself or with regular matter. And so it's not hot. It doesn't bounce around and collide with itself, which is a way to think about thermal energy. So
I take exception to your use of the word boring. That is not boring. Nothing boring about what we don't know about science. Come on. And I agree with Ivan. You know, it may be that the dark matter is something fairly simple that we haven't found yet, but it may also be quite complex. There could be a whole spectrum of particles. I mean, neutrinos are part of it, but we think they're only a tiny part of it, okay? And we haven't got their masses yet well determined either. I'm just, anyway, so there's nothing boring about what we don't know.
I keep thinking about us being like a 3-year-old human. At 3, you have the world. You know everything. You are totally confident and you're aware. And by golly, you know what's going on. Then you turn like 6 and you go, I didn't know anything. And then you become 30 and you go, I know nothing. So I think we're at the stage of development of, we're the 3-year-old scientists. We're out there, we're exploring, we're having a grand time, but we really don't know anything yet. We're working on it. We're pretty good for 3-year-olds.
Yeah, but for the 5% of the universe stuff that we do know, we know it pretty well, actually.
Pretty good.
I mean, you know, people could say, well, since you're so ignorant, maybe we can have spaceships traveling at 100 times the speed of light. No, we're not that ignorant.
So one mystery still to be solved is, why is there much more matter than antimatter?
Yeah.
And, you know, dark matter may have answers for us in that area we don't know yet. And one of the articles that Joanne passed around was about an early report on looking at polarized light in the microwave background radiation, and that this might be a sign of dark matter that's...
I'm extremely skeptical about that. And by the way, yes, as you know, it's not a 5 standard deviation effect, but anyway, there's so many. I tell you my own theory about where the antimatter is. I think the Big Bang, there was a pair, a universe-anti-universe pair creation came out. And all the antimatter is in the anti-universe that is distinctly disjoint from ours. So that's my theory, and I'm sticking to it. But
so the conventional wisdom on that is that there was a difference of, you know, like 1 part in the 12 or something, 10 to the 12, between a fundamental asymmetry between generating matter-antimatter pairs, that there was a very slight and as yet not well explained propensity to generate a little more matter than antimatter. And so when, you know, 99.9999% of all the matter and antimatter that was generated during the Big Bang proceeded to mutually annihilate, and then that energy provided the stuff to create new matter-antimatter pairs. As long as you have a very tiny discrepancy in the generation rates of matter and antimatter, even a tiny discrepancy will cause sort of a snowball effect. And eventually, as that energy dissipates and causes the generation of matter and antimatter, you will have a preponderance of matter.
Yeah, we keep looking for breaks in the symmetry, and so far we're not good at that.
Right. I mean, I agree with Scott, and that is the conventional wisdom. Most physicists would say they believe that actually at the very beginning of inflation, it was symmetrical, but then this tiny asymmetry, with about 1 part in 10 to the 10 or 10 to the 9 maybe, occurred. And then, you know, and then everything annihilated, leaving over 1 part in 10 to the 10, which became our matter. That's what, but we don't have a good theory or any real understanding of that asymmetry, but that's what people think. But I think my theory is better, actually. But I just, the point is, you know, if you have a theory in physics, you should be able to disprove it. And I don't know how
proving it.
Right. So we have examples of this effect. where there's an asymmetry between matter and antimatter. So it has been detected, and it is a small effect, but we know very little about it. It's like, okay, we found an example of it, but it's
Yeah.
not enough to
That-
explain.
That got the Nobel Prize for Jim Cronin as CP violation, charge parity violation in the weak interaction. So the weak interaction is not symmetric between matter and antimatter.
Right.
But we don't understand why that could actually cause the
Yeah, the
No good
Big
reason.
Bang modelers have a hard time amplifying that into what we see now.
yeah.
Well, Dave tells me that we have our audio is working fine on the YouTube channel, but the video has, for some reason, for all of us, the video has stopped. So once again, the technical gremlins are bedeviling us. But I think audio is sufficient for what we've been talking about the past few minutes.
Yeah, we've shown no pictures of the universe.
Yeah, well, Mike did show that picture of the orc,
The article.
and I hope the orc showed up for everybody. If not, you can feel free to search for it. Pictures of orcs, astronomical orcs. And with that,
As differentiated from Tolkien's orcs.
right.
And until they discover that it was a drop of water on the lens of the telescope.
Oh, there you go.
It wasn't bird feces.
Right. Well, I want to thank all of you who have tuned in today and who will be watching this in the future. It really heartens us to know that there's a curiosity about science that has motivated you to tune in. And we'll be here again in 2 weeks.
And hopefully all of our pictures will work.
Right. Hopefully fewer gremlins. But thank you also to Ivan, Michael, and John, who lent their expertise and time today. And take care. We'll see you again soon.
See you guys.
Bye, everybody.